He is risen. Alleluia, alleluia. And very soon we're going to celebrate his ascension into heaven on Sunday. All right, guys. So good afternoon again. So without further ado, let's take up like the homework from yesterday. So let me share here. And my allergies are starting to act up. So that's the season. Yeah. There we go. Let me put this on this side. There you go. Benjamin, late. Okay, so Benjamin will do the first one. Who's left? Ernest is late. Ernest will do this one. Luke. Luke will do this one. There we go. We got them. All right, so they're joining. Yeah, so you had to do 16, as I mentioned on the website, as well as the K-12 email that I sent you. It's not exactly clear here, like what they put an arrow. You're not so sure exactly like what's moving. Is it the coil? Is it the magnet? So that's why I put like the arrow on the top of which object is actually moving instead of doing this like that. But I told you here in 16 is the magnet that moves, and in 17 is the coil that moves. All right, so Benjamin, since you were late, you're going to do like the first one here. So I'm going to do the other ones, but you're going to do the first one. So make sure you annotate it, right? And you're going to tell me in which direction the current is flowing, the induced current. Okay, Luke is doing. Okay, all right. So Luke done this one. Yeah, Ernest is doing
Yeah,
this
sorry,
one.
sir. I just came from TOK.
TOK. TOK. Fear of knowledge. Yeah. Okay. All right. So okay, north. Okay, so I'm gonna wait until. Yeah. Okay, that's okay. Good. All right. All right, so let me take this one here. I'm gonna wait until Benjamin like does the first one here. So let me do this one. So once again here, you are moving the coil towards and using Ryan rule number 2. So you see that the induced current is going this way. So thumb is pointing to the left, right, left this way. So this is north, as he said. That's very good. And you should sort of feel a force of repulsion. So if you feel the only way to feel a force, you should feel a force of resisting you pushing the coil to the left. All right. So in order to have a resisting force, this should be north here. So that's very good. So there's a force of repulsion. Okay, good. So let's go back to this. All right, so as I said, it's the magnet that moves. All right, so the magnet moves this way. So there'll be a change in magnetic field. A change in magnetic field will produce electrical field. If there are metals around, it's gonna. Wow, why did you erase that? Okay, doing it again.
Oh, yeah. Sorry, sir. You said the magnet is moving to the right?
Yeah, it's a magnet. 16 is the
Oh,
magnet. Okay,
okay.
you want
Sorry.
to redo it?
Yep.
Okay, well, redo it, and then I'll pursue here. So this one here, so the coil is being moved away. So the induced current, so right hand rule number 2. So that means that this side is north. Whoops. So this side here is north, so this means it's south. And there should be a force resisting you pulling the coil towards the right. So in order to have a resisting force here, this has to be north. So that there'll be a magnetic force between the coil and the magnet. So resisting you pulling the coil further to the right. So this one right here. So let's see here. So once again, right on rule number 2. So the current is going like this. So thumb is pointing towards the right. So this is north, this is south. And it's the same thing. All right. So this is going to be north as well. So there should be a force resisting you moving the coils towards the right. This one here on the top. So once again, you do this, exactly the same thing. So this is north, this is south. And now you are moving the coil towards the magnet. So in order to sort of feel the force of resistance, this should be the south, so that there will be a repulsive force resisting you moving the coil towards the left. Okay. So Benjamin, okay, so this one here, it's the magnet that you move. All right. So there'll be an induced current, as I said, and wires don't like to have their current being changed, so it will do whatever it can in order to bring this to a stop here. So you should feel a force of resistance. So if you're moving this magnet towards the left, then the coil should output a south pole right here, right? In order to resist, yeah, as he put, in order to resist my moving the magnet. So this is south, this is north, and then you use right-hand rule number 2. So north is this way, so the current is going in the proper. So that's very good, Benjamin. All right, so here it moves again. So so it has to output a north to feel a force of repulsion. You're pushing this magnet in, so there should be something resisting you. So once again, this is north, this is south, right-hand rule number 2. So the current is going that way. All right. This one, so the magnet here is moving away. It's the same situation as this one here. So you should have a south. The electromagnet should induce a south pole here. So north. Once again, you do this, and the induced current will go like this. All right. And then finally, this one here. So you're moving this in. It should feel a force resisting you. So it should output a south and north here. So right-hand rule number 2, north is this way. So the induced current will be in this direction. There you go. All right. All right. Okay. Eric Hugh. Eric will do 19. There we go. That's what happened when you come in late. Okay, so look at this one here. All right, so you're given the direction of the induced current here. So if you follow the current, goes like this, right? Right-hand rule number 2. So north is this way. And then you should sort of feel, so you're moving the magnet. Which way is this being moved? Of course, it's being moved this way, towards the left, to feel a force of repulsion. So what did you put? You put, yeah, that's correct. So that's the right answer here. So it's moving towards. This one here, so you follow the current here. So the current goes behind, comes back in the front. So right-hand rule number 2. So this is north. So in this case here, like the magnet is being moved this way, all right? So you're moving the magnet this way, and there's a force resisting you, right? There's a magnetic force between the north pole of the electromagnet and the south pole of the magnet. So resisting you moving it towards the right. And then finally, Eric Hugh, if you're joining us, you have to do this 19 here. So this one here, so once again, you follow the current. So the current will go like this, right-hand rule number 2. So this is north. So you actually moving this magnet this way, so that there's a force resisting you. Okay, any question for these? Are you good? Good. Manav is not here today. All right, Eric Hugh. So in which direction is the current going through this? Eric Hugh, you can chat. I can see here that you have no mic. There we go. Where is he? Is he up? Is he down? Where's he gone? Eric, oh, Eric, there we go, he's got Mike. Eric, you have to do 19. So which direction the current is going here? Is it going like this section here? Is it coming out of the page or is it going away into the page? Eric, Hugh. Can you talk? I cannot hear you if you talk. No, your mic is on. Eric, Hugh. Hey, chat if you have problems. I don't know. There we go. Chat. Nikki. Yeah, okay. So that's Luke. Yes, me too. I don't know what that's mean. Okay. So Eric, are you there? Woohoo! Can you chat here? Oh, it's gone. Okay, got shy. All right, perhaps he'll be back. He's not off the hook. Okay, so number 20. So number 20. I don't have the diagram here, but let me show you it goes here. So number 20. Let me just clear the annotation here. Clear everything. There you go. Oops. Okay, so what you have here, it's like the drop tower here, right? So what do we have here is that we have, there's a cylinder right in metal. It's made of metal. Q, it's made of metal. All right, and you're right here. And just to make it like a little bit like, this is your cabin here, whatever. But just to make it like a little bit easier, let's pretend here that you're in the middle, right? And you're outside this for now, outside this cylinder here, because it's a little bit easier. I mean, in the picture they showed you like right here. Whoops, they show it like right here, right? And this is what happened when you drop. You're outside the cylinder, right? Just make it like easy here. Like let's pretend you're just right there, okay? Before you enter the cylinder here, the drop tower. Now, this has a magnet, all right? Doesn't really matter here. So the cabin here has a little magnet. So let's pretend here, just for the sake of example, I don't know what it does. Let me see in your textbook here. Does it give you like a North Pole, South Pole? 625. Let me see here. So 625. They give you, yes, okay, they give you south. Okay, all right. So it's south. And all right. Okay, so what happens here is that this thing falls down. There must be a way to keep you from accelerating down to the bottom, right? Because you don't want to hit the ground with a certain speed, all right? Now, if you look at the drop tower, of course, you have like probably cables there, right? But that's not like the major force that slows you down as you drop. As a matter of fact, what happens here is that you have a cylinder in the center, and the cylinder is made up, of course, of metal. So let's say here, this is the cross section here of the metal cylinder, all right? Well, you can sort of think of a metal cylinder as a solenoid with like an infinity of loops, super close together, right? You can always think about this. So what happens here is that So when a magnet falls, there's a change in magnetic field. If there's a change in magnetic field, therefore, there'll be an electrical field. Electrical field, if there's anything here that is metallic, it will set like current. So what happened here is this, is that there will be an induced current in the cylinder, in the metallic cylinder. And it should oppose the motion of the cabin here, the motion of the magnet, because this is what has caused the magnetic field. This is what has caused the electric current to be induced. So since it's coming down here, like the cylinder here has to output like a north, all right? And here it has to be south. In order, sorry. It has to output a south, right? In order to sort of prevent this from dropping even more. Now, when it's in the center, that's the same idea also. It may not be obvious here, so that's why I put it like outside the cylinder. And then you use a right-hand rule number 2. So north is down. So what happens here is that you set a current in the cylinder, and the current is going to go like this. So the current here is going to go likewise. So it's going to be, this is a cross section, right? There you go. Right? So the current is being induced in a cylinder, and this is what sort of caused, for the most part, like the slowing down of you when you come down this drop tower. Of course, the cable is there to help, but that's the main mechanisms by which they slow you down. This is called magnetic braking, and it's very, very, very effective. Very effective. Okay, very effective. So once again, like the cylinder here, you can think of it as a solenoid, and then there's a change in magnetic field. There's an electrical field being produced, and there's a current that will be induced in the tower in such a way as to prevent this from accelerating and moving. All right. So question for this? Okay. Well, okay, so let's go back. Like, here's Eric here. Where's this guy? Eric, you? Are you back? Eric, you? Okay, can you talk here?
Yes.
Okay, so this current here, is it going like here? Is it going out of the page or into the page? At 50%.
It's going into the page, I think.
Okay, so it's going into the page. So you're saying here it's going like this. Okay, why?
Because if you use the right-hand rule,
Yeah.
the force of the magnetic field on the charges
So
in the conductor.
Okay, so let me put, hold on a second. So let me put the magnetic field. So the magnetic field goes outside, goes from north to south. So that's the magnetic field, right?
Yep.
Yeah, okay. And then use right-hand rule number 3. Is that what you do?
Yes.
Okay, so tell me what you did.
Like, how do I describe it though?
I don't know. Just tell me what you did with your fingers.
Okay, so I pointed my index finger upwards.
Upwards.
Yes.
Okay, but the magnetic field is going this way. FBI, right? Whoops, the index is your magnetic field.
Oh,
FBI agent.
I usually use my index finger for the velocity direction. But okay.
The index is FBI. Okay, so the magnetic field is going this way. Okay, and then?
And then I use my middle finger.
Yeah.
As the direction of the velocity.
So it's going up?
Yeah.
Okay, so like this? All right. And what does that tell you?
It's going out of the page.
Out of the page. So are you saying it's going out of the page or is going into the page? Because you told me like into the page.
out of the page, I guess.
Okay, out of the page. Okay. So you're saying that it's going out of the page. All right, so going out of the page. All right. Okay. All right. So does anyone disagree with Eric? Thank you, Eric. Yeah, Madav. Oh, yeah, Madav is here. Yeah.
I think it should
It's a little bit.
the
Just hold on a second, Madav. Let me share. Yeah, you can talk. I'm gonna share again because it doesn't. It was like.
I think for the finger,
Yeah.
the middle finger,
Yeah.
it's the magnetic force, and the magnetic force should be in the opposite direction of the applied force.
Yes.
So if it's
Very good.
going up, then it
Yeah,
should
very
be
good. Okay, so remember here. So what you're doing here is this. You are pulling this up. You are pulling this up. You sign, right? The applied force is up. There should be a force resisting you. So whatever the magnetic force is on the wire, it has to be down. So the magnetic force has to be down. So well, let's see here if it makes sense here. Whoops. So the magnetic force on the wire has to be down, right? To oppose you pulling it up. You should always sort of feel the force of resistance here. So if you use like this, so the magnetic force, FBI, magnetic force, down. The magnetic field is like this. So if I do this here, like the current is actually going away from me. So the current, the induced current is actually going as such. All right. Okay, so FBI here, so exactly like this, right? There should be a magnetic force that will oppose my pulling it up. Okay. Any questions? All right. Max is not here today. Yeah, Eric.
So the answer is, I mean, like, is the current going into the page or out of the page?
Into the page.
Also, okay, right.
Yeah, into the page like this, into the page, as I show you. Right.
So my first answer is correct, right?
Yeah, I know, but I asked you to explain, and then you explained to me, and then I don't know if you made a mistake here, like, you know, and then after you agreed to change it. So
because like if you use the index finger for the velocity, it goes into the page. So I'm a bit confused.
Middle finger is your force, FBI agent. All right.
Okay.
Okay, good. All right. So let's go back to this. Okay, so listen carefully to this. Oh, this is hot today. Okay, so we're going to start look at the experiment that Faraday actually did do. And so what it consisted in the following. So what he had was a coil right here, little coil. And it was connected to the battery here, and then there was a switch. And then on the other side, he just had like a coil with a voltmeter or ammeter. It doesn't really matter, okay? It could be a voltmeter or ammeter. The iron ring here is just to amplify the effect. That's all what it does, okay? We don't need to have an iron ring there, okay? We could do the experiment. You're going to get like the same result, but it's going to be like less intense, right? But by putting an iron ring here, it's just like it's more visible, right? You're going to see like the arrow like moving more, okay? So what he noticed was this. He noticed that when he closed the switch, all of a sudden there was a current being induced in the other coil here, but just for a brief moment of time, and then it would sort of stop. And then when he noticed that if he opens the circuit on this side, for a very brief moment of time, there will be a current be induced in the other direction, right? And once again, it would sort of be very brief and we'll go back to 0. So this is called electromagnetic induction here. So this is an experiment that he did actually show in front of an audience. I have to let you know that in the 19th century, scientists were like the pop stars of the era. I know it's changed a lot. Pop stars of the era. So people would sort of go and pay very big money to go and see those scientists talk. And so when Faraday did this experiment and he showed them like what happened, a lady in the audience, after it was done, right? You could take it was like question period, and a lady got up and asked Michael Faraday, what's the use of this? So Michael Faraday said, "Madam, can you tell me what's the use of a newborn baby?" There you go. So I'll let you think what that means. Okay, so why is it that only when you disconnect and connect the circuit here do you get like an induced current? All right, so by the way, like this side here, you call this the primary side. This side is called the secondary side. Okay, so primary coil and secondary coil here. Okay, so what happened here is this, is that when you close the circuit, current will increase. It will increase in a finite amount of time, okay? It will not go like from 0 amp to, let's say, 1 amp in no time. It will sort of build up, mind you, very quickly, but it will build up until it reaches a steady current. Now, you may remember here that from right-hand rule number 1, whenever you have a current flowing through a wire, it creates a magnetic field around it. Do you remember? Right-hand rule number 1. So what happened here is this, is that when you close the circuit, when you close the switch, the current will increase. And as the current increases, the magnetic field will also increase. So the magnetic field is changing. Aha! We know that if there's a change in magnetic field, it will produce an electrical field. And if there's wires around, it will sort of set a current into it. And this is exactly what happens. So when you close the switch here, the current will increase. The magnetic field changes. So there's an electrical field being generated. And this wire here, the second wire here, will start having an induced current. Now, once the current has reached a steady state in the primary circuit here, the magnetic field doesn't change. If it doesn't change, there's no electrical field. If there's no electrical field, then there's no more induced current. And this is why when you close the switch, you saw that the secondary coil here had a brief moment of induced current, induced voltage for a brief moment of time. Yeah, Jason.
Yeah, so in this example here, are the wires touching the iron ring or not?
No, it doesn't matter. No, as I said here, you can remove this iron ring completely. And this is what was so outstanding here, right? So you had like a circuit at one place and you have another circuit at another place, right? And then it seems that you caused something to happen here, right? And even though it's not touching. So that's why it's called induction. That's why it's so marvelous, right? That's why like this lady didn't get it. But anyway, that's another subject. Okay, so now when you open the switch, once again, the current doesn't go from, let's say, 1 amp to 0 amp in no time. It's very fast, but it gradually decrease. Well, as the current in this circuit here decreases, so does the magnetic field. The magnetic field changes. If the magnetic field changes, then it creates an electrical field. If there's an electrical field present, then a wire, such as this one, will have a current being induced. Okay, and this is exactly what happens. So open the circuit for a brief moment of time here. There's an induced current being created in the secondary coil. And then once it's at 0, well, everything comes back to, so there's no more magnetic field. So no more electrical field being induced, and it goes back to 0. Yes, whoever was this, like Madav?
What is the effect of the magnetic field on the primary circuits?
There is also what is called a self-induction. So when you, as I said earlier here, right? You remember, like current wire doesn't like to have its current change, right? So there will also be, as the current changes in the primary coil, there will also be a resistance to have the current changing. This is called self-inductance. All right. So anyway, Jason, do you have questions?
No.
No. Okay. On you. All right. Okay. So the idea here is this: is that the magnitude of the induced current or induced potential, voltage, is proportional to the rate of change of the magnetic field. The faster the magnetic field, right, from the primary coil changes, the greater the induced current or the induced potential is on the secondary coil. Is that okay? All right, so that brings us to a transformer. So once again, it has nothing to do with transformer like from Hasbro. Okay, a transformer is a device that will sort of change the voltage. If you like, I have this laptop here. This laptop has a battery. If there's a battery, then it works DC. All right, but I'm plugging this into an AC outlet. Now the AC, the voltage from the outlet is about 120 volts. The voltage of my battery is about perhaps, like, I don't know, let's say 8 volts. So there should be a way, when I plug this in an outlet, there should be a way to transform 120 volts into 8 volts, because otherwise the battery will explode. All right. So devices that sort of change the voltage across is called a transformer. And the transformer is nothing else but this. A transformer is nothing else but 2 coils. One is called the primary coil. The other one is called the secondary coil. All right. Now you have a soft iron core to make this like more efficient. And you know what they look like when you. I don't have. Hold on a second here. I have to bring this all here. All right. So when you have like a power cord for your laptop, right? Usually you have like a little box that may be like, rectangular or cubic. Well, this is nothing else but a transformer, and it's heavy because there is this iron core inside. Okay, so that's why it's heavy. But it's nothing else but 2 wires. All right, one coil and the other coil. Okay, this is where you have to be careful here. So what happens here is that, let's say here, this coil here, I connect it to a power outlet. Remember, it's AC, so it's alternating current. It will induce an alternating current in the secondary coil too. In order to get an induced current in the secondary coil, there must be a change in current. If the current stays the same, if I had like a battery here and the current stays the same, there won't be any induced current, because if there's a steady current, then there'll be a steady magnetic field. If the magnetic field doesn't change, then by electromagnetic induction, there's no electrical field being generated, and so on and so on. All right. So just to make things like a little bit like easier here, so let's go back to this here. So what we're going to do here is we're going to plot there you go. I'm going to tell you what this is. So this is time right here. And here, this is the current. Right? So this is the current. Now, if you supply, whoops. if you supply, not this, where's that? If you supply a steady current on the primary coil, okay, so if you supply a steady current, so I'm going to put it in, let's put it in, let's put it, what color? Put it in green, there we go. If I supply a steady current on the primary, what I'm going to get on the secondary is nothing. There won't be any induced current in the secondary coil because there's no changing magnetic field. Magnetic field around the wire will not change. No change, no electrical field being generated. So I'm going to get no, whoops, I'm going to get nothing. And there we go. So there won't be anything right here. Okay. Now, in contrast, if I supply on the primary side a current that is increasing at a constant rate, right? So it's increasing at a constant rate. Let's say here, right? Whoops. So if I supply a current that increases steadily, so the magnetic field will change. The magnetic field will change also at a steady rate. And remember what I said before. Why is it I always... The induced current the induced current or the induced potential is proportional to the rate at which the magnetic field changes with time. Well, if the current changes at a constant rate, so will the magnetic field around this wire will change at constant rate. So this will be a constant. Therefore, the induced current will be steady. So I'm going to have a steady current. All right, so I'm going to have a steady current. So let's pretend here it gives me something like this. Yeah, there you go. All right. Now, what about if I sort of change the current in the primary coil at a greater rate? All right, so let's do this here. So let me choose a color here. Let me choose blue here. So what about if I change it still at a constant rate, but it's higher in the primary coil? Now, can anyone sort of guess what will happen? What will happen to the secondary coil? If I change the, day.
It'll still be constant, but it'll be higher than
That's
the
correct.
red one.
Yeah, that's correct. That's exactly it. All right, that's exactly it. Okay. Now, can anyone sort of tell me the relationship that exists between those two here? Right? Between the primary and the secondary? Mathematically? Mathematically? Madav?
Is the slope of the primary equal
That's
to
it.
the magnitude of the
Exactly.
secondary?
That's correct. It's the slope. Right? So the induced current, right? So the induced current is proportional to the slope of primary current. Right? Slope of primary current. with respect to time. That's exactly it. Okay. So the faster the current changes, the greater the induced current will be. Okay. Okay. So the induced current there you go. I'll use your. So the induced current is proportional to this. Right? That's what it is. Okay, so you got that. Very good. Okay, so let me check here what message was here. Okay, that's my son. Hold on a second here. Let me tell him. There we go. Apologize for this. All right, good. Okay, so we go back to this. So in order for a transformer to work, in order to have induced current, you must send like current that changes, right, on this side. Okay. Okay, I'm gonna sort of skip this here for now. All right. I'll come back to this if I have time at the end, but I want to talk about, yeah, probably I'll have time, but I want to talk about this here. Like this one here shows you like if you send like this current in the primary coil, this is what you get in the secondary coil. And you can see here that this graph here is exactly the derivative of this one, right? So at first, the slope is very high, so the induced current is very, very high. At the top here, the rate of change of current is 0. Therefore, the induced current is 0, right? And then when it comes back down, well, now the slope is negative, so the current in the secondary coil will change direction, all right? So that's what's up. But anyway, we'll come back to this in a second. Okay, I want to do something a little bit more, not more useful, but something that, so that you can do the problems. Okay, so as I said here, a transformer is a device that changes voltage. Okay, there's two types of transformer. One is called a step up, and the other one is called a step down. A step up transformer, this is what it says. A step up transformer will take the voltage in, the primary voltage here, and will boost it up. All right, so a step up transformer, the voltage on the secondary side is higher than the voltage on the primary side. And this all depends only on the number of turns. This all depends on the number of turns. If you want to change the voltage, the number of turns in your coils have to be different. The number of turns in the secondary coil is called NS. The number of turns in the primary coil is called NP. And so happens that the voltage is proportional to the number of turns. So Vs over Vp is equal to Ns over Np. Now, the number of turns in the secondary coil over that of the primary coil is called the turn ratio, the turns ratio. So you have a step-up transformer when the turns ratio is greater than 1. If you want, instead of boosting the voltage, you want to reduce the voltage, such as when I plug this laptop in an outlet, I want to go from 120 volts to 8 volts. So you have to have more coils, more turns on the primary side that you have on the secondary side. When you have this, then the voltage on the secondary side will be smaller than the voltage on the primary side. And the turn ratio, there's a mistake here. The turn ratio will be smaller than 1. So make sure that you amend this. All right. So this one here is smaller. Okay. So not higher. Okay. So make sure. Oh, it doesn't show up because like it. I don't know why it's so. Let me just share. I don't know why it's so laggy. There we go. All right, so the turn ratio is smaller than 1. Now, yeah, Dave. Yeah, Dave.
I forgot to put my hand down. Sorry.
Okay. Now you might sort of think, oh, well, that's good. We have more, we can get like more voltage out of smaller voltage, right? It seems that you gain energy for nothing. So energy is always the same, right? So remember here, so the power is equal to I times V. Remember this? So here, this is the power that comes in, the primary side. This is the power that comes out. So power in must be equal to power out by conservation of energy, right? The energy in must be equal to the energy out. Now, this would be true for a 100% efficient transformer, but we don't have this, right? So some of the electrical energy coming in, of course, will be transformed to thermal energy and not electrical energy. So it won't be always like, it won't be 100% efficient. But we're going to present here it's 100% efficient. So the electrical energy coming in is equal to the electrical energy coming out. If you divide by time, you'll get the power. Power in is equal to power out. PP, so that's the power in the primary side, is equal to power in the secondary side. Now this is equal to IV, and then if you do this, this is what you get. So what you notice here, you notice that the voltage is inversely proportional to the current. So in a step-up transformer, your voltage will increase, but then your current will decrease. A step down, so this is what it says here, right? So step-up transformer, VS is greater than VP, but the current in the primary side is greater than that on the secondary side. A step-down transformer is the other way around. So your voltage output will be lower, but the current will be higher. Okay, hold on a second here. Oh, well. All right, so. Okay, you good for this? All right, so let's do a very simple problem here. This is not like really, really difficult. So let's do this problem together here. A step-down transformer contains 2,000 turns on the primary coil and 200 turns on the secondary. The potential difference in current in the primary coil is 30 volts AC, because you remember, in order for a transformer to work, I must send a current that changes with time, right? I cannot still send a direct current. So this voltage here is fluctuating. 30 volt just means it's like the maximum probably, right? So 30 volts AC and 0.7 amp AC2. What are the values for the induced potential difference in current in the secondary coil? Well, it cannot be like any easier here. So you write what you're given. So you're given the voltage on the primary side, which is 2,000. You're given the turns of the secondary. Whoops, I forgot this. The turn on the secondary is.
Sir, isn't it 30 volts?
Yeah, sorry. You're correct. It's primary, it's 30 volts. Thank you. The current is 0.7 amp. You have 2,000 turns on the primary, and you have 200 turns in the secondary. And you're looking for VS and IS, right? Well, since the voltage is proportional to the number of turns, so what you have VS over VP is equal to NS over NP. So VS is just equal to VP times NS over NP. And then you just put like the values here. So it's 30 volts times 200 over 2,000. So that will give you 3 volts. So this is a step down, well, that's what it says. It's a step down transformer because the voltage went from 30 volts to 3 volts. All right. Now for the current, you can use either the fact that the current is inversely proportional number of turns or inversely proportional to voltage, doesn't really matter here. So if we do this here, IS over IP is equal to VP over VS. So it's inversely proportional. So IS is equal to IP times VP over VS. And I will give you 0.7 amp times 30 volts over 3 volts. And as expected, the current is greater. All right. So this was a step-down transformer. So the voltage went down, but the current went up. Okay. All right. So let me send a message here again. Okay. Apologize for this. There we go. All right. Are you good? Okay. You're gonna have problems with this. Something that you need to know is the following. By the way, does anyone know what the symbol for transformer is? Anyone guess? No one? Yeah, Max?
Wait, do you mean like this transformer or like the robot head?
What's that? Like
Wait,
a
do you mean-
robot? No.
Wait, so would it just be like a big T or something?
What?
Would it be a capital T?
No. I'm going to show you where it is. The symbol is this. As a symbol. It's like your two coils. Primary coil, secondary coil. It's not very well done here, but okay. So, all right. So that's the symbol for a transformer. Okay. So when you do problems here, the primary side. Okay. So let me make this a little bit better. Okay. So hold on a second. So this is. All right. So that's the symbol here. When you do the problems, the primary side is always connected to the power outlet, okay, or to the battery. To the EMF source. All right. And well, it's going to be an outlet. It has to be changing, right, current. So it's not going to be a battery. And the secondary side here is always connected to your load. All right. So for instance, here, like my computer, the primary side is connected to the EMF source, the outlet, and the secondary side is connected to the computer. So that's my load here on laptop. Okay. It's really bad here. I should do it. There we go. There you go. That's
Sir.
right. Yeah.
But in this case, right? So there's space between the primary side and the secondary side. But when you brought up your computer example, what would be that space in between?
It's this here. So it's, you remember, like you have like a little it's a little square, remember? Right? Your adapter. It's like square or rectangular. It's a little heavy, and this is what it has. So it has a core. It looks like a rectangle here. And you have one coil on one side and the other coil on the other side. And that's the space here.
So inside of that like little like thing that we like plug into the outlet, it has this thing in it?
Yeah.
Oh,
That's exactly what it has. Yeah. Exactly. Okay. Are you good?
So there's some stuff in the chats.
Yeah, Jason.
Wait, so what causes the alternating current to turn to direct current?
So because a computer is a battery, right? So so the current has to go from AC to DC. Well, this is so once they transform the voltage, let's say from 120 volts AC, it goes to, let's say, 8 volts AC. Now there's another device here that will sort of make sure that the current goes in only one direction. So it's a device. I'm not going to sort of go over it, but it's a device that will sort of make sure it's constant. Yeah, Dave.
So are both the transformer and that device in that block, like the block of
There-
plastic?
Just repeat this.
So there's a transformer that changes the voltage, and then there's the other device that turns AC to DC. Are those both in the block in the power
Yeah.
line?
Yeah,
Okay.
correct. I think so. I'm not so sure. Yeah, I think so.
Yeah, they
But
are.
I may be wrong. I think they are. If you want, well, I'll try today. So I'll check. I have a voltmeter, and I'll check the output, and I'll see if it's constant voltage. So if it's constant voltage, then so it means that it's both devices are in one. Yeah, Forrest, perhaps he knows. Yeah.
It depends on the device, but most of them have the rectifier and the transformer together.
Yeah, and the transformer. Yeah, a rectifier. Yeah, that's what it is. Yeah. Thank you. All right, so let's go back to this here. So I promise I would sort of come back to this. Okay.
Sir, there are some questions in the chat.
Yeah. Oh, those chat. No, just look, put like APSFDSFTW. What does that mean?
Oh, I might have asked a question, and Claire asked. If
Oh,
she can
Claire,
repeat.
well, if she has to leave, she has to leave. She doesn't have to. Is it equally correct to see transformer can be used to change current as well as voltage? Yeah, yeah. Look, I have no idea what this means. What does it mean, Max Yang? EWAP, what's that?
Oh no, because she said she has an AP test, so I'm like,
Oh.
ew, AP sucks. Yeah, that's what
AP
I'm
sucks?
Or,
Is that what you said?
well, no. I just said ew, AP, because it's like ew,
How come you have AP, guys? You're taking like AP too? Anyway, good luck. I thought they were talking about tank ammunition. I have no idea what this means. Like, look, okay, you're losing. Okay, so if we go back here, so this is your coil right here. I'm going to sort of make this a little bit bigger here. So this is your primary coil. Right here is the primary coil, and this is the secondary coil right there. And you can see here that in this case here, the current in the primary coil is increasing with time, and it's going this way. And it will generate a secondary current on the other side, an induced current here, that is going in this direction here. And at this particular moment here, so if you look at the slope, so if you look at the slope here, so the secondary current will have an induced current corresponding roughly, it's proportional to the slope, right? Okay. And when the primary current here is about to decrease, right? So it's an alternating current. So the current goes up in the primary coil, and then it it starts decreasing. So at this point here, there's nothing in the coil. There's no induced current for a brief moment of time. And then when it starts to decrease, now your slope is negative. So what happens here is that the current in the secondary coil will go in the other direction, right? And as the slope becomes steeper and steeper, of course, the magnitude of the current will get like bigger and bigger and bigger. And then here, when it reaches its maximal slope, this is when the current in the secondary coil will reach its maximum value. Then when it starts to decrease, the current in the secondary coil will start to decrease. And then right here, when it reaches its maximum, and then starts to decrease now. Don't forget that here, like the primary current is going in the other direction here, right? And then it's going to sort of flip the current in the secondary coil. The key point here, I want you to understand here, the secondary current is out of phase with the primary current, right? There's a 90 degree shift between the primary current and the secondary current, okay? All right. Okay, I think that's it for today. So make sure that you do the homework for today, and then we'll take them up tomorrow. And tomorrow I will talk about how electricity is being generated, transported, and I'm going to talk also about application of electromagnets. And then and I'm going to sort of go back to this definition that I gave earlier. Not this. This one here. Okay, it's a little bit laggy, but it's coming. So I'm going to talk about, so far we did the problem using this. But now I'm going to talk about, tomorrow I'm going to talk about this one here. The magnetic field of induced current always opposes the changed magnetic field that is causing the induced current. So we'll look at Lenz's law from this point of view here, okay? And then from this, we'll be able to figure out, we'll be able to figure out like this little diagram here. Why is it that like the current here the current in the secondary coil goes one way, and then it goes the other way, and then it goes the other way, and so on. So we're going to explain this. Okay, so questions? All right. So I'll see you tomorrow at 10:30. So be there at least 10 minutes before. Don't be late, because you might may ask you like to do some problems if you're late. All right. So I'll see you tomorrow, and God bless.
Bye, sir.
Bye-bye.
Bye, sir.
Thank you, sir.
Bye.
Yes, sir.
Bye.
Bye, sir.